Is it audible? Hello? Can you hear me?
Yes, sir, you are audible.
Okay, thanks. So today we'll discuss limit point compactness and locally compactness. So recall that compact, what is the meaning of compactness? A topological space X is said to be compact if every open cover, so let me write X as union of open set, arbitrary open set, U alpha belongs to A, if such open cover admits a finite subcover. So we may, instead of taking all those open sets, we may take only finitely many open sets, maybe denote it as U1, UN from this collection, such that X can be written as union of this U1 up to UN. If this is possible, then we'll call X is a compact set. We'll define compactness in this way. Now, there is another notion which is called limit point compactness. So let us define point compactness. A topological space X is called limit point compact if every infinite set has a infinite subset of this topological space, infinite subset has a limit point. So this definition is weaker because the thing is that compactness will imply limit point compactness, but the converse may not be true. Okay, so let me define another notion. This is called sequentially compactness. X be a topological space, it is said to be sequentially compact if every sequence has a convergent subsequence. So the interesting thing is that all those kind of compactness, limit points compactness or sequentially compactness, all those compactness are same if X is a metric space, then compact imply limit point compact, and this will also imply sequentially compact. And this direction is also true. Sequentially compact imply compact. Therefore, all those things are equivalent. Compactness will imply limit point compactness, and so if something is limit point compact, then that is compact, and that is also sequentially compact. For a topological space, which is also metric space. So those are few properties. So is this definition clear? What is limit point compactness? This property is also known as Bolzano-Weierstrass property, or maybe it sometimes it is called Bolzano-Weierstrass compactness, because we know for real number satisfies this kind of properties. Bolzano-Weierstrass property. Okay. So let us solve a question. The question is something. It is slightly different. Closed 01. We are considering closed 01 as a subspace of Q. Subspace of Q. Now it is true false. Is it limit point compact or not with respect to lower limit topology? So Q, what is the lower limit topology? We know R can be equipped with a topology where the bases are of the form A comma B. Okay, A less than B. This kind of basis. If we consider this kind of basis, then the topology generated by this basis, suppose B equal to this kind of thing, then topology generated by B is called lower limit topology on R. Okay, this is actually closed 01, this interval. Now the question is the interval closed 01, is it limit? It is limit point compact or not? This is the question. Let us see what happens here. So note that lower limit topology, this is not a metric space. So though this seems so in metric space, all those kind of compactness are same. So in this case, limit point compact may not imply compact. Okay, this is what we need to remember. So let us see what happens. So in this case, consider this set 1 minus 1 by n. N belongs to the natural number. So this is a subspace of 0, 1. Here there is a slight mistake because finite set, okay, infinite set I have already written. Every finite infinite set has a limit point, because finite set may not have any limit point, right? It depends on the topology. So that is important. Infinite set. Otherwise, the definition does not make any sense. Okay. Now our claim is that though A is an infinite set, this is infinite, it is clear, but we'll prove that this set has no limit. Okay. So let us see what happens. So let me draw the set. It will look like something like this. 0 to 1, we are considering this interval. So it starts with this 0, 1 minus 1, then 1 minus half will be half, then 1 minus 1/3 will be 2/3, and it will converge to 1, right? This is what it is. Now we'll prove that if we consider any x from this closed 0, 1, then that will not be a limit point. Okay. So x belongs to closed 0, 1 is not a limit point of A. So we are considering this the topological space closed 0, 1 with respect to lower limit topology. So what is happening here? Let us see. So x belongs to close 0 1. That implies x is greater equal to 1 minus 1 by n and less than. So x belongs to something like this. Here, for example, here, so it is in between half and one third. So this must be true that x is greater equal to 1 minus 1 by n and 1 minus 1 by n plus 1, right? Then this is for some n belongs to natural number. Now we are considering lower limit topology. So x comma 1 by 1 minus 1 by n plus 1, this is the neighborhood of x, right? A neighborhood of x. Now we can see that this neighborhood, let me denote the neighborhood by u, right? U say, then u intersection a, u intersection this topological space, sorry, this a, this topological space x minus the singleton point x is empty, right? That is u intersect, you can see the set u only intersects at x, this point. Sorry, u may intersect. We are considering a point like this. So u is not intersecting with any point from this set. A is the set. This 0, half, one third like this. For example, if we consider x equal to half, then we are considering the interval like this, half to one third. So you can at most intersect at this point, half. But if we don't consider half, then the intersection is empty. So the intersection can be at most half, but we are removing that point. So the intersection become empty. So you can see that the neighborhood can intersect at most one point. But if we don't consider that point, then the intersection becomes empty. From here, it is clear that x is not a limit point. Limit point. So we have already considered from this to this. Up to this, we have already considered. Now, the remaining part is to consider the point 1. So up to close 0 1, everything is considered. 1 is remaining. 1 is remaining. So let me see what happens if we consider 1. So the question is, x equal to 1, is it a limit point of the set A? Sorry, this is not x, this is A. We are considering this set. It will intersect, it will always intersect. We are considering this limit point of the set A. Okay, sorry. So again, the same kind of issue will occur. So for x equal to 1, what is happening? For x equal to 1, you can see that 1 belongs to this interval. 1 belongs to 1. But this 1 is also open with respect to lower limit topology in this case. Why? Because you can see 1 can be written as closed 1, comma open 2, intersection with the topological space x. So intersect with x, only 1 will get the singleton set 1, right? Therefore, the same kind of issue is occurring in this case. 1 intersection with a minus x. So we are trying to see if 1 is a limit point of a or not. So we are considering a neighborhood, and the neighborhood does not intersect any point other than 1. So the intersection is 1. So if we remove 1, then the intersection becomes empty. So So from here we conclude that 1 is not a limit point of limit point of A. So we have successfully constructed an infinite set which has no limit point, right? Therefore, A has no limit point in X. So in this topological space, we have constructed an infinite set which has no limit point. Therefore, it is not a limit point compact. So the answer is false. Okay. So we have already seen in previous class that there is another notion which is called locally compactness. Now again, compact will imply locally compact, but reverse is not in general. So what is locally compact means? It means for locally compact at X. This means if we consider the point X in the topological space X, there exists a compact neighborhood of this point. Compact neighborhood means it means if we consider there should exist a neighborhood such that that neighborhood contains a compact set. Okay, this is the definition. Sorry, I think I have written in a wrong order. It will be something like this. X belongs to some open neighborhood U, and U containing some compact set. So this K is called compact neighborhood. Why neighborhood? Because it already contains an open set, open neighborhood, right? That's why we are calling K to be a compact neighborhood. X is locally compact at X if there exists an open set U and a compact set K of X such that this happens. Then we'll call X is locally compact at X, and if this property holds for all those points, all points of X, then we'll call X is a locally compact topological space. Now the interesting thing is that if something is locally compact, then we can add a singleton point and we can make the topological space a compact space. So let me write the theorem. So it is very useful theorem. X is locally compact. CPT means compact. I am denoting it by CPT. Hausdorff. Hausdorff also denoted by T2 space. Space if and only if there exists a topological space X hat. I am denoting the topological space, a new space by X hat, such that X is contained in X hat. The second property is X hat minus X is a singleton point, singleton set, and the third property is X hat is compact Hausdorff. Okay, so this theorem says if we consider a locally compact Hausdorff space, then add a point X is locally compact, add a singleton point, take take the union, then this will become a compact space. So this is always possible. Okay. So and moreover, if we consider another X set, moreover, if Y satisfies all those three properties, then X hat is homeomorphic to X. So those X hat will be homeomorphic to that new another space Y. So if Y satisfies all those three properties, then that Y is also same as this X hat. And this homeomorphism is extended by identity map. That means, so X can be included in X hat, right? And X can be also included in Y, because Y satisfies all those three properties. This property is also satisfied by Y. Then this, from X hat to Y, we get a homeomorphism. And moreover, this diagram commutes. Okay, this is what means extended. This homeomorphism is extended by identity. So this is, so from here we get the notion of compactification. So let me write explicitly compactification. Consider X a topological space which is a subspace of Y. Subspace. And Y is compact plus Hausdorff, such that closure of X is Y. Then Y is called compactification of X. So it means X can be embedded in a compact space, right? And this compact space arises by taking closure. So X closure becomes Y. So if this happens, then that Y, the superset is called compactification of X. So add some points, and the space, the topological space become a compact space. As add all those limit points, and it becomes a compact space. If this is hold for that Y, then this Y is called compactification of X. Okay, and moreover, if Y minus X is a singleton point, let me denote the singleton point by a point star, then Y is called one point compactification. Okay, so the previous theorem says a locally compact Hausdorff space, it is always possible to get one point compactification of a locally compact Hausdorff space. So this is the theorem. In this case, so note that X hat minus X is singleton point. So that X hat, this property is satisfied by X hat, right? This is okay. Now X bar closure of X is Y. So we need to see only this property. Okay, so we'll see this property. And Y is compact Hausdorff. It is already there. It is compact Hausdorff. So all those properties are already there. So we only need to see that closure of X in this X hat, this is same as X hat. This property we need to check. Okay, so the how to prove this theorem? The idea is this idea of this theorem. So this x hat is x union a singleton point. Let me denote it by some star or some infinity. Okay, and topologize x hat by defining open sets. So what are the open sets? One choice is open sets of x. Okay, so take all the open set of x, and another choice is x hat minus k, where k is compact subspace. K is a compact subspace of x. Okay, that means this is same as x minus k union the infinity. So those are the open set in x hat. Take all the open set of x or x minus some compact set, but you need to take infinity in this case. So those are all those choices. So this is called one point compactification of the topology. So why this is compactification? We only need to see that closure of x is x hat in the topological space x hat. We need to see that because in this case x is already contained in x hat, right? So we only need to see that closure of x is x hat. So this is clear because since infinity is the one that extra point is a limit point of x, right? This infinity is the limit point of the subspace x. So closure is x union infinity, which is same as x hat by definition. Up to this, is it clear? Everything is clear or not? So can you see that infinity is the limit point? Because if you consider a neighborhood of infinity, then open set of x that cannot contain infinity. So this is not a possible neighborhood. So only possible neighborhood will be like this, right? And note that so this neighborhood will be x minus some k, x minus some compact set. So it must contain infinitely many elements. So the neighborhood contains a point other than infinity, because x minus compact set can be, it may not be infinite, but x minus a compact set is, it contains some points other than infinity. So this is the whole point. So this theorem says one point compactification of a topological space is always possible. Just include a point and topologize the space by the following. This is how we can topologize this new space x hat, and this new space becomes a compactification. And this is one point compactification because we have only added a singleton point. Okay. So let me see some example of locally compact Hausdorff space. So note that R is locally compact Hausdorff space. Locally compact Hausdorff, LCH. Locally compact, H denotes Hausdorff space. R is LCH. Why? Because any point for X, it belongs to some neighborhood like this. Some X compact neighborhood, X minus epsilon, comma X plus epsilon. So this is compact neighborhood. Why? This is closed bounded, so compact in usual topology, and it also it also contains a neighborhood of X. So therefore, X minus epsilon, this is a compact neighborhood. Example of locally compact Hausdorff space. And similarly, we can see Rn is also locally compact Hausdorff space. The same idea, right? Instead of X minus epsilon, comma X plus epsilon, let me denote it by U. Then for this kind of point, in this case, x1 up to xn, there the point will look like this, and take all those neighborhood x1 minus epsilon, x1 plus epsilon times this. So this containing u1, or maybe denoted by k. So this will be containing some k1 times k2 up to kn. Okay. So those are locally compact Hausdorff spaces. Non-example. So one non-example will be R to the power n. So note that though those are not compact, those are locally compact. We can always find a compact neighborhood. Okay. Now what is Rn? Rn means take product of R infinitely many times, countably many times. In this case, it is not locally compact. Why? Because if we consider a point, that point has a neighborhood like this. A basis element of Rn will look like this. It will be B, which is A1 comma B1 times A2 comma B2 up to An comma Bn times, uh, except finitely many open sets, open something open intervals, all those should be R. This is how compact topology is defined. The basis element will look like this. So you may choose U1, U up to UN arbitrarily, but after some finite set, all those elements should be same as those R, whatever product we are considering. Okay. Now, if it contain in sorry, content in a compact set A, then B, then what happens? Then B is contained in some closure of B, and that closure will also contain K. Because K is compact, this is Hausdorff space, so it is already closed set. Therefore, closure is the smallest possible closed set which contains B, right? So that B bar will also contain K. Now the problem is this is closed subspace of a compact space. This is compact. This will imply B bar is compact. Now what is B bar? B bar will look like A1 B1 closed interval times A2 B2 up to n bn, then r cross r like this. Closure will look like this. So closed subspace of a compact space means it is compact. We know this is always true. So that means therefore b bar, this b bar is compact. Since b bar is closed subspace of a compact set, this b bar is compact. Now the problem is this is a contradiction. Why? Because if this is compact set, then if we project on the n plus 1 component, so consider the projection map phi n plus 1 from this Rn to R. Okay, phi n plus 1 means if we consider these tuples xn n, then pi n plus 1, if we apply pi n plus 1 on this becomes the n plus 1 component, right? So in this case, you can see that image of b bar pi n plus 1, this is continuous map by definition of product topology. So pi n plus 1 of b bar, this is n plus 1 component, which is R, but R is not compact. This is continuous map, but under the continuous map pi n plus 1, the image is not compact. Image of a compact set should be compact, right? So this is a contradiction. This is, we have assumed this B bar is compact. That implies R is a compact space, which is a contradiction. Hence, R in R to the power this n is not locally compact Hausdorff space. So we need to see if Q is locally compact or not. Earlier day we have started, but we cannot finish. So the answer is false. So why this is false? Because we'll see that there is no compact neighborhood. Okay, if you consider any point, it cannot have any compact neighborhood. So we have started with a compact. We'll prove that this kind of set, this is not a compact subspace. So first we'll note that this is a closed subspace. Why this is closed? Because it is complement of this kind of open set. So this is closed subspace of Q, right? Now, as a subset of countable set, this X is countable. Sorry, this X is countable. We can write X equal to Q1 up to Qn, like this. But what is the problem here? So this is not compact. Why? So proof of this fact, this is not compact. The proof is simple. If we consider this open cover, so let ui equal to this a closed a comma open qi. Okay, then this ui I belongs to n forms an open cover of x. Okay, but if we don't, if we only consider some finitely many ui, then it cannot cover this x, right? It may cover up to some qn, but it will not cover all those q1 up to q1 q2 up to goes on, it goes on. So this open cover has no finite subcover. Okay, but it has no finite subcover. Therefore, the topological space X is not compact. Now if we consider any point, for example consider 0 belongs to Q. Okay, so if possible, let 0 has a neighborhood, 0 has a compact neighborhood, compact neighborhood K. Then there exist open sets, open set minus epsilon comma epsilon, such that 0 belongs to this minus epsilon comma epsilon intersection Q containing K. So this intersection with Q, otherwise this is not a subset of Q, so we must intersect. So 0 belongs to this open set, but note that, but this will imply 0 belongs to minus epsilon by 2 comma epsilon by 2 intersection Q containing K. So this is a closed subset. This is already not compact. This is not compact. We have already proved this is not compact in star by star. But this is a closed subspace of a compact set. But this is closed subspace of a compact set, which implies this is compact. Is compact. So it is a contradiction. This is not possible. This is not compact and simultaneously compact. Those are opposite things, which is not possible. From here, we conclude that Q is not locally compact. The problem occurs because we have assumed that 0 has a compact neighborhood. So similarly, we can prove each point has, instead of 0, the same idea goes on for any point. It is not locally compact at any point like this. So in this case, we are considering that epsilon is irrational. Otherwise, we have already considered this A is irrational. Epsilon is irrational. This is a consideration. Otherwise, we cannot use star. Okay. So we need to see if which of the following are correct or not. So the question is, if f is continuous maps from x to y, then x is compact will imply fx is compact. X is locally compact implies fx is locally compact, and similarly other compactness. So let us see the first one. So recall that answer. Option A is okay. A is true. Why? X is compact, then under a continuous map the image is compact. Why this is true? Because consider an open cover. Suppose fx, consider the open cover u alpha for fx. We need to prove this u alpha, this open cover u alpha admits a finite subcover. So f is continuous, therefore f inverse u alpha are also open. Then this is the proof. F inverse u alpha, those are open. This is open cover. This u alpha, those are open cover of then f inverse u alpha is open because f is continuous. And moreover, note that x is union of f inverse u alpha, right? So this implies, and since x is compact, so by compactness, x can be written as, there exists some finite subcover, so f can be written as f inverse u1 up to un, I equal to 1 to n. Okay, this will imply x fx equal to, just apply f. Okay, fx equal to u1 union un. So we get the that open cover u alpha admits a finite subcover. Okay, finite subcover. So compact imply that image set will be also compact topological space. Now what about locally compactness? If x is locally compact, then will it imply fx is locally compact? So for B, consider the identity map from this discrete topology, Q with discrete topology, to Q with usual topology. Okay, then the left hand side is locally compact. This is locally compact. Why? Because take any point, let Q belongs to Q, right? Then Q belongs to, Q has a compact neighborhood. Why? Q belongs to the open set Q. This is open, and this Q also contained in Q, and Q is closed, compact, right? Because every take any open cover, it has finite subcover. Q itself is a finite subcover. Any open set has a finite, because open cover means it must contain Q, and take that singleton, because any set is open in this case. Take that open set. So Q has a compact neighborhood, singleton Q. This is true for all Q. Therefore, Q with discrete topology is compact. But we have already seen but Q with usual topology is not compact, right? We have already seen this fact in this first question. Q is not locally compact. Sorry, those are locally compact. Local behavior. Okay, so we see that though domain is compact, the image set is not compact. Okay, so locally compactness may be preserved by continuous map. Now option C. In option C, it is given f is open. Then locally compactness imply the image set is locally compact. Let us see. So f maps x to y. This is continuous and open map. Now, and x is locally compact. It is also given. So we need to see if the image set is locally compact or not. So consider the image set, and suppose suppose y belongs to this image set fx. Okay, and we need to see if this y has a compact neighborhood or not. So y belongs to fx means y equal to some fx for some x belongs to x. Now take a compact neighborhood x belongs to some u contained in K. Okay, so this is open neighborhood of x. Then this will imply fx belongs to f of u. This is contained in f of k. Now image of a compact set is compact. This is compact because f is continuous. Image of a compact set is compact. And this fu, this is open. Why? Because f is open. So for the point fx, we get a compact neighborhood f of k, right? Therefore, this image set fx is locally compact. Any point, take any point y in the image, it has a compact neighborhood. Okay, so C is okay, A is okay, B is false. Now what about D? It is given that X is limit point compact. Will it imply fx is also limit point compact? So let us see what happens for option D. And continuous, and X is limit point compact. So the answer is not. So counter example, let us see the counter example. So consider x equal to r cross the set 0, where r is equipped with usual topology, and this closed this set 0 comma 1, this is equipped with indiscrete topology. So indiscrete topology means the only open sets are either empty set or the whole set 0 comma 1. Okay, so if we consider the product topology, then the map f from this r cross 0 1 to this r by sending f of x comma 0, let f equal to this, fx comma 0 equal to x, fx comma 1 equal to 1 x. Let fx to f be the map defined by this. Defined by this. Then f is continuous. Why this is the case? Take, because f inverse of u, where u equal to open in R, this is same as u cross 0 1, right? Because both x comma 0 goes to x, x comma 1 also goes to x. Therefore f inverse u becomes u cross 0 1. But this is open because this is open set, and 0 comma 1, this is open with respect to this indiscrete topology. We have considered indiscrete topology in the second component. Therefore this is open product topology. So f is continuous. Okay, this is the reasoning. Now we we'll see that the set R is not limit point compact, right? Every infinite set may not have a limit point. Okay, that is true for compact spaces, compact subspaces, compact subspaces of R. So R is not a limit point compact space. Since just a minute. Okay. So R is not a limit point compact space. Why? Because the infinite set, the infinite subspace N has no limit point. So the limit point set of N is empty. Okay. So therefore R is not a limit point compact. So in this case, the image is not a limit point compact. Now we'll prove that X is limit point. Though X is limit point compact, the image R is not a limit point compact. Okay. So claim is R cross 0, 1 with respect to product topology is limit point compact. Okay. So what is the proof? Proof is very simple. For example, take uh, let A be a subset of X, subset of R cross 0, 1. If X comma 0 belongs to A, then X comma 1 is a limit point of it. Why? Because by definition, what is the neighborhood of X comma 1? It will look like U cross some open set cross 0, 1. Okay, and therefore X neighborhood of X comma 0 will look like U cross 0, 1. Since X belongs to U, therefore X comma 0 and X comma 1 both belongs to U cross 0, 1. By product, it will look like some square, right? Both will be inside U cross 0, 1. And by the same reasoning, if X comma 1 belongs to A, then X comma 0 is the limit point of A. So not only for infinite set, every non-empty set, every non-empty subset of R cross 0, 1 has a limit point. Okay. Therefore, R cross 0, 1 is limit point compact. Okay. So we are done. So this is false. We have constructed a continuous map such that the domain is limit point compact. Though the domain is limit point compact, the image, which is real number with usual topology, is not compact, is not limit point compact. Okay. So let us see question number 4. There are lots of questions in this question. So we need to identify one-point compactification of the following spaces. Okay. So the first one is open 0, closed 1. So note that this is locally compact plus Hausdorff space. because this is subspace of real number. Real number is already locally compact, right? Therefore, the subspace. Uh, so, in general, subspace may not be locally compact. The problem, for example, Q is a subspace of real number which may not be locally compact, which is not a locally compact. We have already proved. But for open zero closed one, we can explicitly see that this is locally compact space, and this is also Hausdorff. Take any point, it has a neighborhood that closed interval that is a compact neighborhood. So it is already a locally compact Hausdorff space. And subspace is always Hausdorff space, subspace of Hausdorff space. So can you add a point and make it a compact topological space? Just adding a singleton point, it becomes a compact space. So answer is yes. Just add singleton. So this is A. So A union this singleton 0, which is this interval. This is compact space. Compact. So let A hat equal to A union 0. So this is compact. A hat minus A is a singleton set is 0, and moreover, so those two property is holding in this case. And there is another thing we need to see, that so we are using that theorem how to make uniform compact, how to make one point compactification. We need to see all those three properties: x containing x hat minus x is singleton point, and this the last one, compact Hausdorff space. Sorry. So this is singleton set, and so the first property is a containing a hat. This is okay. Second property is a hat minus a is singleton point, and the third one is a hat. This is compact, and it is also Hausdorff. We are considering closed 0 1 with respect to usual topology. Okay, then this becomes a compact Hausdorff space. By all those three properties, it is clear a hat is one point compactification of it. Okay. Now what about the second one? Closed 0 half, comma open half, comma 1. Close 0 1, close 0 half, union half, comma 1. So in this case, the problem is, so in this case it is okay. So take, just include half. Take, let a hat equal to a union the singleton point half, which is 0 comma 1. So it satisfies all those three properties. First one, a containing a hat, it is okay. The second one, a hat minus a is singleton point, and the third one is a hat is compact Hausdorff. Therefore, a hat is one point compactification of A. Now let us see the third one. In third one, the space, the given space is closed 0, open 1, 1, 2, and 2, 3. So if we add 2 points, include 1, and include 2, then this becomes 0, 3, this closed interval. So a closed bounded set of real number is compact. So this becomes a compact space. Those are compact. Let me write why this is compact. Because closed and bounded subset of R. This is compact because of this. So if we include those 2 points, 1 and 2, then this becomes compact topological space. But in general, if we, we need to just add 1 point and make it a compact space. So adding 2 points is not allowed. So what modification can be done? So let us see what can be done in this case. So note that 1, 2, we can bend 1, 2 this interval into a circle like this, punctured circle. Okay. So why? Because 1, 2, this is homeomorphic to 0, 1. What is the map? T goes to t minus 1. Okay. This 0, 1 is also homeomorphic to circle minus a point. Circle minus singleton set. Right? Circle, just remove north or south pole. What is the map? In this case, the map is t goes to e to the power 2 pi it. Then e to the power 2 pi 0, which is 1, will be not there. So it is like this. Geometrically, what is happening? This is 0, this is 1, 2. We have just shifted 1, 2 to this 0, 1, homeomorphic to this 0, 1. Now, this we have bended this 0, 1 into this circle in R2, right? So the only thing is that this point is not there. Okay, S1 minus this singleton point. Okay, subset of R2. So S1 as a subset of C or R2, whatever we say. Then those two things are homeomorphism, because we can explicitly write the map in the reverse direction. For example, for this circle to 0, 1, this is log, the function log function, and this is just, instead of subtracting, add 1. So we can write the inverse continuous map. So those are homeomorphism. And moreover, note that this 0, 1, so the thing is that A is homeomorphic to this topological space. A is homeomorphic to this punctured circle. Punctured circle means the point is not there. This punctured circle, so the point 1 is not there. Okay, S1 minus the point 1, this point is not there. Now what we can do is simply add two line segment. One line segment is corresponding to closed 0, 1. So this closed 0, 1 can be shifted here, and similarly this open 2, 3 can be shifted here. Okay. So again, the homeomorphism will be like this. For for this part, for 1 comma 2 we have already defined the homeomorphism. For this disjoint part, close 0 comma open 1, just shift accordingly. Okay. For example, let me write explicitly close 0 comma open 1. Let me denote the homeomorphism by f. Then f restricted to open 1 2 is e to the power 2 pi it, this function. F restricted at close 0 open 1 is the above this line segment, right? So this part is 1 and open 0 1 is this, sorry, close 0 open 1, this rotated into this part and shifted. So this is actually one plus I times t, and f restricted at 2 comma 3, this portion applied on t. So 2 comma 3 will be there, so it is 1 minus it, sorry, minus it, but one minus I t times minus 2. So 2 comma 3, that can be mapped here 0 comma 1, and by subtracting 2 it becomes 0 comma 1. Then by rotating minus I times t minus 2, that becomes this interval, and then again shift by plus 1. Okay. Similarly, this should be, no, this is okay. So we can see that 0 becomes 1, and in this case 3 becomes, sorry, 0 should not becomes 1, 0 should becomes this point, which is 1 1 plus I, right? So this a slight modification is needed. The problem is this 0 1 is not directly rotated. This part should moves here. So a different homeomorphism is needed. 0 should becomes I. What modification can be done in this case? 1 plus it t at zeros, it should becomes 1 plus I. So that can be explicitly written by linear function, but means at 0 it should becomes 1 plus I, and at 1 this should becomes 0. That is, this interval should move here. This linear function, we need this linear function. So let me denote fz equal to, suppose fz equal to az plus b. So at 0, f of 0 is 1 plus 1. So 1 plus I equal to a times 0 plus b. So b is 1 plus 1, 1 plus I. So this part is 1 plus I. And at 1, f of 1 means 0 equal to a times 1 plus b. So b is 1 plus I. So this is minus 1 minus I. minus 1 minus I. So this is the homeomorphism we need. Okay, rough work. So this homeomorphism is needed. Similarly, we can verify that one. A verification is needed. This, for example, at t equal to 2, it is 1, this point, and at t equal to 3, it is 1 minus I, which is this point. So this is already okay. So this homeomorphism, from this homeomorphism, it is clear uh, the given subspace, it is homeomorphic to this kind of topological space. So everything is there, but the point 1 is not there. So if we add 1, this will become compact, right? Because it is closed subspace of an Euclidean space. So A union, so let me denote this image. So let B equal to F. Okay. Then B union the singleton set 1 is a compact subspace of R since it is closed and bounded. Closed bounded subspace of Euclidean space. Okay, therefore it B hat is compact, and we can see all those properties are satisfied. So B hat is 1-point compactification of B. 1-point compactification B hat with usual topology. Okay, this is 1-point compactification of B, which is homeomorphic to A. Okay, so if we need to find 1-point compactification of a topological space, we can just compactify a homeomorphic space. Okay, so instead of compactifying that space directly, we can always modify the space by homeomorphism, and we can compactify the image of this space under the homeomorphism. So those two are same, because a theorem says if A and B are homeomorphic, then 1-point compactification are also homeomorphic. A hat and B hat will be homeomorphic, and moreover, there is a commutative diagram like this. So instead of finding this, we can directly find. Instead of finding 1-point compactification A hat, we can directly find B hat, because this B hat will be homeomorphic to A hat, uh, extending this homeomorphism. Okay. So B hat is also 1-point compactification of A up to homeomorphism. Because the thing is that 1-point compactification are same. If there are two 1-point compactification, those are homeomorphic. So instead of finding A hat, we can find B hat. So let us try few other problems. For example, D is the same problem. There is no difference. So I have in this problem for C, I have constructed some non-trivial homeomorphism, but instead of making this kind of complication, we can simply rotate the circle and shift so that only origin is removed. Then the problem becomes more easier. So in this case, the image will be this. So those maps will becomes easy to construct. Just shift. For example, this close 0, 1, this will be shifted here, right? That is subtracting 1, and similarly open 2 3, this can be shifted here, just subtract 2, and this 1 2 can be made here using the exponential, but again we need to modify this exponential. For example, we need some rotation, for which here some multiplication, those kind of thing would be done. So we can directly use the homeomorphism, because s1 minus 1, that is homeomorphic with this space, right? So we can do the problem in this way also. Now let us see what is the 1-point compactification of natural number n. Problem number E. Note that natural number n, this is locally compact Hausdorff space, it is okay, there is no issue. Now n is homeomorphic to the space x, where x equal to 1 by n. N belongs to natural number. Okay. Why those two are homeomorphic? Let f map n to x. Define fx equal to 1 by x. So this is continuous, and the reverse direction map g from x to n is again the same map, gx equal to 1 by x. So f compose g and g compose f, both are identical. Both are continuous and identity map. Their composition are identities. Therefore, f is a homeomorphism. Okay. So instead of compactifying n, we can compactify the topological space x. So what is the compactification of x? So we note that x is not compact. X is not even closed, right? 0, the limit point is 0, which is not there. So add that limit point. So include 0. Let x hat equal to x union 0. So if we add the singleton point 0, then this becomes closed subspace and also bound. Okay, this is not closed. But if we add 0, this becomes closed and it is already bound. Therefore, x hat is compact. Closed bounded subspace of real number, Euclidean space, is compact. Okay. So x hat minus x is a singleton point. Therefore, by those three observations, x hat is 1 point. X hat is an 1 point compactification of x. Hence, x hat is also 1 point compactification of the set of natural numbers. So the next question is s1 minus 1 0. So s1 minus the point 1 0. 1 0 means the point on the x-axis is removed. Okay, this point is removed. So just add that point. Then it will become a compact space. So it is very easy. Just add the point 1 comma 0. Add that singleton point. Now option for G, it is x1 minus 1 0 and 0 1. X1 minus 1 0 and 0 1. So point is removed. So let me draw the picture. So this point 1 comma 0, this is removed, and 0 comma 1, this point is removed. Okay. So the thing is, again, this is very easy. So we note that, so there are two curves. one curve is this portion, C1, another curve is this portion. So C1, C2 both are homeomorphic to interval. So the disjoint union both are homeomorphic. C1 is homeomorphic to interval, open interval 0, 1. C2 is also homeomorphic to open interval 0. Okay. The same kind of idea you can use, that open 0, 1, just apply e to the power 2 pi it. So if we apply e to the power 2 pi it, it will cover the whole thing. But to cover only this portion, e to the power 2 pi it by 4, this will work. So this will only cover quarter of the circle, right? Similarly, for this portion, you can just apply three-quarter of that, and you can rotate accordingly. So in this way, you can prove the homeomorphism. This direction is easy, e to the power 2 pi it by 4. This direction is trickier. Here we need some kind of modification. Some rotation is needed, which is also easy. So both are homeomorphic to 0, 1, and open 0, 1 and this both are homeomorphic to circle minus a point. We have already seen this fact. So this is circle minus a singleton point. This is also circle minus a singleton point. Therefore, this becomes the topological space, that first one is this circle, this is homeomorphic to this circle minus this origin, right? Something like this. And the second curve is also homeomorphic to this circle minus the origin. Okay, both origins are removed. Okay, so now it is clear. Just add the origin. So this is not closed because origin is not there. Origin is a limit point of the set which is not there. Just add origin. Okay. So suppose this set is y. Y. Then y hat is y union the origin 0, 0. Okay. This is closed and bounded, therefore compact. And y hat is 1 point compactification of y, hence of x. Okay. Up to homeomorphism, y hat is also 1 point compactification of x. Up to homeomorphism. This is not 1 point compactification of x, but homeomorphic to that 1 point compactification. So this is also clear. Now what about open disk in R2? Let us see open disk in R2 is what is the 1 point compactification of? So this is open disk in R2. So everything is there, but those are not there actually. So those boundary is not there. Okay. So this is the open disk. Now we need to see what is the 1 point compactification of this space. B0, 0, this point, comma 1. Unit open disk we have considered. Which is a subset of R2. So we need to add a point such that this becomes a compact. This is not compact because those boundary points are limit points which are not there. So this is not a closed subspace, which is therefore not a compact topological space. So we note that this space is homeomorphic to something like this. This space is homeomorphic to this pair, unit pair minus north pole. So unit pair minus north pole. Why this is the case? Because we can always use this stereographic projection method. So using stereographic projection, so note that this is homeomorphic to R2, right? What is the homeomorphism? Send Z to Z by 1 minus mod Z like this. So this is the homeomorphism. Okay. Now we can compactify one one point compactify this topological space R2 because those two spaces are homeomorphic, and we know that stereographic projection, this gives a homeomorphism between R2 and topological space, the topological space unit sphere, right? So this point will be mapped here. So the homeomorphism is okay. So S2 minus 001 R2 is homeomorphic with this. Send the point x comma y to that stereographic projection formula 2x by 1 plus x square plus y square. We can explicitly prove this is easy to see. Just take a ray and just calculate where the ray intersect with this corresponding to x comma y, where the rays intersect with the sphere, and the coordinate becomes this 1 plus x square plus y square minus 1 plus x square plus y square by 1 plus x square plus y square. So this is the homeomorphism. Okay. The reverse side is also easy to calculate. So now from this example it is easy to see which point is needed to add, right? So this equal to ax. Then a hat equal to a union 001. If we only include this point, which is pair, is compact, right? Therefore, a hat is 1 point compactification of open unit disk up to homeomorphism. Okay. So this is how we can solve those kind of problem. 1 point compactification and limit point compactification, etc. So let me stop here. We'll continue in the next Friday. Okay. Thank you.